Hey, in this video, we're going to do the opposite of what the last video had us do, which was instead of calculating Kc, we're going to determine the equilibrium concentrations from it. In this problem here, we have methane gas combining with water to produce carbon monoxide and hydrogen gas. And this is all going to take place in a 0.32 liter flask at 1200 K. At equilibrium, the flask contains 0.26 moles of carbon monoxide, 0.010 moles of hydrogen gas. So let's actually maybe add this to it. 0.091 moles of, oh, that was the H2. I'm going to back up. It has 0.26 moles of carbon monoxide and 0.091 moles of the H2 gas and 0.041 moles of methane gas. What is the water concentration at the equilibrium? So here is what we're trying to figure out, the water concentration, and we know Kc. Well, this one is not one of the problems that we use a Rice table for, because Rice tables are when we have change, when we're not at equilibrium and moving toward it. In this case, we're already at equilibrium. So, looks like we have a situation where we can write the equilibrium concentration, or equilibrium expression, right? So we have carbon monoxide concentration times the H2 concentration cubed divided by CH4 times H2O. And we can put the H2O in here. It's not liquid water, it is gaseous water, so we can include it in the equilibrium expression. And it looks like H2O is our unknown, and we have Kc. So we could rearrange everything, solving for the H2O concentration, right? So if we solve for the H2O concentration, and we did like a cross multiplying, we would have that's equal to the carbon monoxide times H2 cubed divided by CH4 times the Kc. And here we can plug in the concentrations. Now, the thing that you need to be aware of is these numbers that were given to us in the problem, these are moles. And of course, brackets mean molarity concentration. So we do have to convert everything to molarity units, and everything is in a 0.32 liter flask. So let's plug that in. The carbon monoxide concentration, right, was 0.26 moles per 0.32 liters. The H2 concentration was 0.091 moles divided by 0.32 liters, and this is cubed. We're dividing this by the methane concentration, which is 0.041 divided by 0.32 liters. And now we're plugging in the Kc value that was given to us in the problem, 0.26. And when we plug that into the calculator, we should get an H2O concentration of 0.56 molar. Let's take a quick look at the question again. What is the H2O concentration at equilibrium? Yep, 0.56 molar. We could also double check this, right? We could also plug these values back in using water, right? And double check our answer using 0.56 to determine if, in fact, we do get this Kc value of 0.26 back out. So that's how you would do a problem like this, solving for one of the unknown concentrations, in this case water, when you do have the Kc.